Hi everyone. So to really complete our description of how the Standard Model works, we have to discuss how the weak force fits into this quantum field theory framework. And you remember that the photon is used to describe quantum mechanically Maxwell's equations and the interaction, the electromagnetic interaction. Essentially, it's very simple. You've got a plus and a minus charge. You're done. Now, the strong force, we had to kind of twist things a little bit in order to make it work. We had to invent this three-dimensional color charge. But once that was done, we were able to kind of explain some of the unique features of the strong force as well. Well, in order to shoehorn the weak force into this quantum field theoretical structure requires a bit more work. And the fundamental idea to realize is the title here. The weak force, what it does is it actually transforms the very nature of these particles. And so this Feynman diagram, what it represents is a neutron decaying. So this is how we would now incorporate. Well, we're now able to incorporate in a Feynman diagram the way that neutron decays, which we talked about a long time ago when we introduced the nuclear forces. And so remember, the neutron inside of it has got two d quarks, one u quark. The proton's got two u's, one d. So really, what's different about the neutron and the proton is that the d quark inside, one of the d quarks inside the neutron is changing into the proton. And that's what we mean here, is that this is actually a manifestation of this transformation of the fundamental particles. We've actually moved, if you remember that periodic chart, we moved up and down the periodic chart. We moved from the d to the u level in this neutron decay. That's mediated by a release of one of these weak bosons, which we just kind of postulate. We know we want some sort of boson to be in the middle of this process. So we imagine this happening. The crazy thing about this guy is it has to be charged, because we go from something that has to be electrically charged. We go from something with 0 to a +1 charge, right? So the W boson has got to carry a -1 charge in order to maintain the conservation of charge. So this is not only mediating a weak force, but also an electric force. So that adds to the complication as well. But set aside this detail about the charge. We just want to focus on the weak nature of what's going on here. So this boson exists, and it actually propagates for a while and decays. Now, this isn't the only way the weak boson works, but we're talking about how neutron decay works, and this is the picture. This is the situation. Basically, the neutron falls apart, becomes a proton, and spits out a W particle, W boson. That W boson itself decays into the electron we see and the neutrino that was discovered as a consequence. And so, if this were a Feynman diagram, one of these would have to be an antiparticle. And so that's why we actually say that the production here is not so much a neutron, but an antineutrino. That's a detail. The important thing is that what happens is that the W basically flips the D into a U and exchanges the neutrino and the electron characteristics. So we go up and down that periodic chart. We move up and down through the quarks. We move up and down through the electron and neutrinos. Those are called leptons. And so we move through the leptons and the quarks. And actually, this chart shows all the various different combinations that are possible. We can move to the left and right. This would be up and down on that original chart. This is the U quark, the D quark, C, S, V, and T. And so we can actually move all the way through in various combinations based on the energy level and the various characteristics of these different particles. The boldness or the dottedness of these lines indicates the relative probability or strength of the various reactions occurring. So D usually, well, D has to go into U, but let's take the top quark here, for example. T usually decays into B, occasionally decays into S, rarely goes straight from T all the way down to D. All of these eventually fall into the U. You know, this whole chart kind of flows in that direction. The only reason we have D's is because the proton cannot have all three U's in it. We can't have a U. And the reason for that fundamentally is because of the Pauli exclusion principle. We can't have three U quarks in a particle because we can only have a pair with anti-parallel spins. And so the proton is actually the most stable particle of all. It's got two U's and one D because of this extra Pauli exclusion principle. And that, as a shortcut paper, is how the weak force transforms the different particles and essentially is the way in which the weak force is mediated in this quantum field theory context.